Okay, in our previous video, we talked about what it means for a vector field to be conservative, and that means that it is a gradient of some function. So we want to show, we also discussed how to test for that, and I didn't say much about the actual test. But we did see that if we have a vector field FGH in R3, and it's over a simply connected region, means the region doesn't intersect, the curve doesn't intersect itself, and you can complete a closed curve inside the region where all the points stay within the region. In space, F, G, and H have continuous partials. So just some preliminaries of what we need in order for this to work. A test to see that the function is conservative is all these kind of different mixed partials are equal to each other. If we're dealing with vector fields in R2 only, we need that the partial of f with respect to y is the same as the partial of g with respect to x. So in this video, we're going to talk about why this ought to be the case. Not really what it means yet, but we'll build towards that. And I'm going to show you a way to remember this test that might be a little bit easier for us and significant approach. Okay, so first let's suppose, so here's the rationale behind why this test should work. If f is a conservative vector field, then there's some function, let's call it phi, such that f is the gradient of phi. If f has the following components, f, g, and h, that means each of these components is really a partial derivative of phi, since phi is the potential function whose gradient is f. So that means that the partial of phi with respect to x is the first component, partial of phi with respect to y is the second component, and partial of phi with respect to z is the third component. Right, so this is like a little f, little g, little h. Now, let's take a look at the first piece of the test, right? What does that really tell us? What is that? Why does that ensure that we have a conservative field? At least 1/3 of the reason why we do. Let's see. Let's actually figure out what df dy is. So that means we're looking at this component, and we want to find the partial of f, which I've written as phi, with respect to y. Okay, well, that's just going to be a second order partial of phi, first with respect to x, then with respect to y. Sounds good. Now let's think about what dg dx is. I'm going to do this one in pink. So that means that I'm looking at the second component of my vector field, and I want to take the partial of that with respect to x. So I'm going to go ahead and do that. So partial with respect to x of d phi dy, well, that's going to be a second order partial of phi with respect to x, then with respect to y. Now, we know that these two are equal to each other because they are both mixed partials. We know that mixed partials are equal by Claro's theorem. And so we're basically saying here, okay, if we test those mixed partials and they're equal to each other, that means that we're coming from a vector field whose components are derivatives of some potential function. That's what we're checking. Same thing happens with the other two equalities, right? If we look at the other two equalities, let's check. If we, for example, consider, let me do this one in green, what partial of f with respect to z looks like. Well, if we're thinking of f as a conservative vector field, we know the component is a derivative, partial of phi with respect to z. Oh no, I did the wrong one. Sorry, I did the wrong one. I mean, we're looking at this component now with respect to z. So if I take the partial of the first component with respect to z, that's going to give me a second order partial dz dx. Okay, if I look at the other piece, let me do this one in blue. Partial of the third component with respect to x, well, now I look at that third component, take the partial with respect to x, and that's going to give me d phi dz. That's going to give me the second order partial of dx dz. Well, these are equal to each other by Clairaut, so it makes sense to test that they're in fact equal to each other to make sure that we have a conservative vector field. So what we're actually doing is we're testing what these really are right here, is we're testing the mixed partials to make sure that they're equal to each other. And if they are, that's going to mean that our vector field is a conservative vector field whose components are partial derivatives of a potential function. So that's what that test means. Now, we're going to look, one last thing in this video is something called the del operator. So how do we remember how we check all these partials, right? Well, let's take a look at the del operator. This is the same operator that we used when we took partial derivatives. Oops, I misspelled that. And it's going to help us, it's going to come up a lot in the next few days. But the del operator is an operator that can be represented as a vector whose components just do the operation of taking partial derivatives. That's what the components do. So it's an operator, not a function. It operates on a function, a scalar function, or on a vector. We've seen that when this operates on a scalar function f, we get the gradient. And now we're going to do something slightly different. We're going to say, all right, we're going to take this del operator and I'm going to do a cross product of the del operator with the vector field f. And our vector field f will be in R3 and its components are just f, g, and h. So we know how to do the cross product. In the first row, we're going to line up our I hat, j hat, k hat. Then in the second row, this is what's going to be a little different. I'm going to put the components of this operator, whose goal is to take partial derivatives with respect to different variables. And in the third row, I'm going to put my functions that are the components of the vector field, f, g, and h. So let's see what happens when we actually carry out this cross product. Well, we're going to have our component I, and this is going to do, we're going to do the partial derivative of the third component h with respect to y. So that's going to be dh dy minus the partial of g with respect to z. Okay, minus j. All right, this time we're going to look at the partial of x with respect, no, the partial of h with respect to x minus the partial of z, f with respect to z. And then plus k, and here we're going to have the partial of g with respect to x minus the partial of f with respect to y. And notice what these components are. These components are exactly our test, right? They're exactly the difference between these partials in our test. So if dh dy equals dg dz, then we know that this component's going to be 0. If dh dx equals df dz, then we know that this component is going to be 0. And if these are equal to each other, this component will be 0, which means that this gives us the 0 vector. All right, so our test really, to test whether we have a conservative field, and we're dealing with a field in R3, then show that this operator del cross f gives you the 0 vector. And that's a really nice way to remember how to do this test. This has significance, some geometric significance that we'll discuss later on. I'll tell you now, just as a foreshadowing, that this del cross F is called the curl of the vector field. It's actually a microscopic circulation at a point, or circulation density. We'll talk more about that, but we see here that a field is conservative if del F cross F equals the zero vector. In R2, we could do that also. We would need to convert our field to a field in R3 by letting the k component be zero, or we can just remember that, this one's a little bit easier to remember, that we just do our mixed partials, make sure that they're equal to each other, and just check that.